governed by that phase lock loop circuit. So in terms of the efficiency of the channel, synchronous communication is much better. Okay. This is more details about, there's an example of an Ethernet frame, and typically the preamble, if you were sending one frame followed by another frame followed by another frame, you've got the preamble between them, but effectively it would amount to only 2 to 3% of the time on the serial wire. So much more efficient. Anyway, you don't need to worry about the details of that. You will not be tested anything to do with Ethernet on this course, okay? So don't worry about Ethernet. Okay. You are expected to know the difference between synchronous and asynchronous serial communication. You'd be expected to know the difference between full duplex, half duplex, simplex, and we need to know a little bit more about how serial communication works inside the 8051, which is what I'm going to do now. So the 8051 serial communication system is an example of an asynchronous serial communication system. In terms of the 8051, let's rub some of this out. I've drawn this before, but I'll just remind you. There are 2 pins on port 3 which are used for receiving data and transmitting data. For the life of me, I can't remember which ones are which. So, but you're probably expected to know that kind of thing. And they're both connected to a pair of registers which collectively share the same name, SBUF. Okay? And associated with this, there's also a special function register called SCOM. And so this is be the TXD, and this is the RXD. All the inputs and outputs on the 8051 effectively are what we call TTL compatible. So if it is sending something out from SBUF out onto the transmit wire on your serial communication system, remember this is an example of a full duplex serial communication system. So if this is one microcontroller, you've got data going this way. This would be the TXD, which, well, it's TXD here, which would be connected to the RXD on this device. That didn't sound very healthy. In the other direction, you'd have the TXD here wired up to the RXD on this one, and then you'd have some kind of shared ground wire between them. So to build, I hope your computer's all right. To build your complete bidirectional communication system, we need 3 wires. 1 wire for communication in this direction, 1 wire for communication in this direction, and then some kind of ground reference point. And between the 2 8051s or whatever it is, you could be receiving data and transmitting at the same time. That's why it's full duplex. What else do I want to say about that? Now, a lot of computer systems, now we're saying logic 1 on the transmit interface, if it's TTL compatible, logic 1 means a voltage of about 5 volts. Logic 0 we represent by about 0 volts. There are lots of serial communication systems out there where logic 1 and logic 0 aren't those voltages, they're different voltages. So it might be, for example, as we can see here, so a 1 is represented in RS232 thing as -3 to -15 volts, and a space, i.e. a logic 0, is represented as +3 to +15 volts. What this means is if you've got an 8051 serial communication system and you want to connect it to something that is what's known as RS232 compatible, so you've got a device that understands the serial communication protocol according to standard RS232, do not connect them up directly because the voltages are not the same. If you want to connect an 8051 to a device which has a serial communication system, an asynchronous serial communication system that is compliant with RS-232, you need to put a converter chip between the 8051 and the RS-232 compliant device. The good news is actually there are devices which are very cheap that basically, in terms of power supply, all you need to give it is 5 volts and 0 volts, and it will generate these other voltages for you on the chip. So that's that. There's a couple of slides now about the details of RS-232. I'm not going to test you on anything to do with traditional RS-232, so don't worry about this. It's just basically saying this is the data tunnel equipment and the data communication equipment, and this is traditionally how you wire them up in RS-232 language. But you can basically see the transmit on one device is connected to the receive on the other, and vice versa. Yeah.
If it's not compliant, how would the external chip know?
It's up to you, the designer, to not plug them in.
No, the external chip you get to convert.
Yeah.
How does it know what it's converting if it's not compliant?
It assumes that on one side of it you're giving it TTL signals, and on the other side of it, it will generate things which are compliant with RS-232. If you basically wire it up, so for example, on the input side it's not TTL, it's something else, it may well blow up. Okay? These things are pretty dumb, you know. That's why we have engineers. There are, now, in a real RS-232 system, it's more complicated than I've mentioned so far, because yes, you have the transmitter and the receiver, but in addition to that, there are other signals that link up these two devices, which are used for handshaking purposes. And that's what these things are. So, for example, ready to send is basically the transmitter side of it saying, you know, I want to send something. Clear to send is a signal from the receiver side of something saying, if you want to send me something, you're allowed to send it to me now. If you're using these handshaking signals, and you will not be tested on any of this, so don't worry about it, but if you were to wire up like an 8051 to something that was an RS-232 compliant interface, if it's using handshaking and you want to send something to that device, you would have to check that it's sending you the signal clear to send. That basically it's saying, okay, I'm now ready for you to send me the information. And if it doesn't send you that signal, then you should wait until it does. So handshaking is used to ensure that the transmitter doesn't prematurely send information when the receiver's not ready for it. Now, remember, in a full duplex communication system, there are 2 transmitters and 2 receivers, because each entity is both a transmitter and a receiver. So that's why on this particular device you can see a ready to send and a clear to send. And there is additional handshaking as well that's available. Now, if you are connecting your now the 8051 does not support these handshaking signals as part of its hardware in the serial communication system. You could add this functionality if you want to using extra pins on the 8051, but you would have to write the software to do the handshaking. That's not provided for you. Generally speaking, we just don't bother. But if you have an 8051 system and you have some other system over here, if this system expects you to use handshaking and you're not using it, it might have data to send you and it's not sending it because it's waiting for you to tell it it's clear to send it. So what you would have to do is to configure that other system and say, I'm not using handshaking. I only use the transmit data, receive data, and that's it. So don't bother with any handshaking. An example of this might be, for example, if you're using a PC, which not all true of all modern PCs, but certainly PCs as of a couple of years ago, most of them had RS-232 compliant serial interfaces, which was a little D connector at the back of it. By default, they would normally use handshaking. So you could use that connector to connect to your 8051 system, and you won't see anything happening because unless you say, you know, the clear to send, nothing's going to ever be sent to you. The solution is on the PC, you would tell it to configure its serial interface to use no handshaking. Let's just do one more slide, I think. So generally speaking, when we're connecting up our microcontroller system to something like a PC, we just configure the PC to say, don't bother using handshaking, because actually the 8051 doesn't support it unless you want to write your own code to do it. And then you're just making use of the transmit data and the receive data. So TXD on the microcontroller goes to the RxD pin on your PC and vice versa, and you just need a common ground. Right, there's an example of this MAX232 device that converts between TTL logic, this is the TTL side, and this is the RS232 side. And the nice thing about this is it only uses 5 volts and ground and a few capacitors, and it makes those -3 to -12 volts and all that kind of stuff for you, as if by magic. Okay, let's just do one more slide. So, over here we have SBUF. If you write to SBUF, automatically, because SBUF is it's actually 2 registers which are kind of glued together. If you write to SBUF, it will automatically go into here, as if by magic. How do you write to SBUF? You say, move the contents of the accumulator, move the contents of the accumulator into SBUF. Remember, source and destination. The process of doing that, we'll put it in here. As soon as anything's written to SBUF, it will automatically be transmitted. Okay? When it's finished transmission, there is a flag called TI, which will become high. But only when it's finished sending the information. Okay? So what you would do, write to it, and then you would, first of all, you would set TI to be low, you write to SBUF, and then you keep testing TI, for example. When it goes high, you know whatever you put in here is gone. And then you can send the next thing. Okay? On the receive side, you don't know when information is going to come in. It's an asynchronous serial communication system. You don't know when the other entity is going to send you something. But when it does come in, effectively, there is a flag called RI that will go high if some valid information is in this buffer ready for you to read. If you ignore this and some more information comes in, the new information will overwrite the old information. Okay? So it's your job to keep monitoring this to make sure you don't miss anything. Now the good news is both RI and TI can be linked to interrupts that we did a couple of weeks ago. So you can be sure not to miss anything. When this flag goes high, effectively it's your job to read from SBUF. So what you would simply do is say, move into the accumulator, the contents of SBUF. It will not read back what was in the transmit side of here, it will read what's in the receive side of SBUF. So far so good? The one thing I'll say to finish this off is, well, how do we know when to sample the data that's coming in here? And on the transmit side, how do we know at what speed to be sending the information out on TXD? That's right. That's all under the control of the serial control register, special function register, and you can choose this to be various means of generating that clock. The most normal way of doing it is we use one of the timers to do it for us. So next week, we're going to carry on with this, and I'm going to show you how to configure the timers in order to generate information so that it will be sent out at precisely a certain rate. And if it's coming in, you'll sample it at the right rate. So we'll do a little bit of maths, not much, just to configure the serial interface. So it won't take us long. So on the Wednesday lecture next week, which will be going ahead, we'll finish off the serial interface, and then we'll move on to the next topic that we're doing, which I've forgotten already. Anyway, have a good weekend, and see you on Wednesday.